we have developed some very, very important ideas about systems, ideal gas, in terms of relationships between quantities that describe the gas, the energy of the gas. Now, what I'd like to do to finish up this course is to look at some extremely important results. We know that for mechanics we have Newton's laws. Newton's three laws are kind of the fundamental laws of mechanics, and they help us understand what's going on in the motions of objects, things like that. That's where we started out the course. What I'd like to do to finish up the course is take a look at some fundamental laws that deal with thermal properties of systems. These are called the laws of thermodynamics, and there are 4 of them. Just like Newton's laws, sometimes we refer to Newton's laws as Newton's first law, Newton's second law, Newton's third law. With the laws of thermodynamics, they are also numbered. We've got the first law of thermodynamics, the second law of thermodynamics, the third law of thermodynamics, and not the 4th law. Actually, there is one more, but it's so fundamental, it's called the 0th law of thermodynamics. And we're going to go through them in that order. We're going to look at the 0th law, then the first, second, and third law. And that's what we're going to do to finish up this course. So, the 0th law of thermodynamics. Okay, the laws of thermodynamics. I hope you don't mind me using this overhead. It's a very old overhead. I've been using it for years. If you are a typically aged college student right out of high school, this overhead is older than you are probably, so I hope you don't mind me using it. The laws of thermodynamics, the 0th law of thermodynamics. 2 systems individually in thermal equilibrium with a third system are in thermal equilibrium with each other. So what does this mean? 2 systems, let's call this system A and system B. If 2 systems, A and B, are in thermal equilibrium with a third system, we'll call this system C. So if A and B are in thermal equilibrium with system C, then A and B are in thermal equilibrium with each other. Okay, let's take a look at a kind of a diagram and see what this means. So here we've got 3 systems. A and B are in thermal equilibrium with system C. Now what does that mean? Well, for A and B to be in, for A and C to be in thermal equilibrium, it means that first of all they are in thermal contact with each other, which means thermal contact means heat could go back and forth. So heat could go from A to C, or it could go from C to A. Thermal contact means heat exchange is possible. Being in thermal equilibrium means there is no net heat flow. So there is no total heat going from A to C, nor from C to A. C and B are in thermal equilibrium, and that means the same thing. They're in thermal contact, and there's no net heat flow from C to B, or from B to C. If this is true, the 0th law tells us then, if we were to put A and B in contact with each other, so we put A and B in contact with each other here, then what we know is that they would be in thermal equilibrium with each other, meaning no heat would flow from one to the other. Well, what is this telling us? If 2 systems are in thermal contact and no heat is going from one to the other, what that means is they must be at the same temperature. In other words, if system A is at temperature TA and system C is at temperature TC, these 2 temperatures must be equal to each other. If one had a higher temperature, then we would expect, if TC had a higher temperature, we would expect heat to flow from C to A. Or if A was at a higher temperature, we would expect heat to flow from A to C. To be in thermal equilibrium then means that the temperatures must be the same. Likewise, system B and system C are in thermal equilibrium, which means that the temperature of system B must be the same as the temperature of system C, because no heat is going between those. Well, if this is true and this is true, then what do we know? We know that the temperature of system A must be the same as the temperature of system B. The 0th law of thermodynamics basically allows us to use temperature as a thermodynamic property that is useful in this sense, that when 2 things have the same temperature, it means they could be in thermal equilibrium if we put them in contact with each other, meaning no heat would go from one to another. if two things were at the same temperature, we put them in contact and heat went from one to the other, one would cool down, one would heat up, and then they'd have different temperatures. That's not what we think about as being in thermal equilibrium. So the zeroth law, which is the reason it's such a fundamental law and called the zeroth law, is it talks about it's about some very, very fundamental idea of what it means to be in thermal equilibrium, and it allows us to use temperature as a quantity to measure some property of the object. Okay, very good. What's the next law? The first law of thermodynamics is basically a statement of the conservation of energy as it applies to thermal properties of systems. The first law of thermodynamics: the internal energy of a system changes from an initial value, U sub I, to a final value of U sub F due to two different processes. Due to heat, Q, and work, W. And the relationship between the change in the internal energy is delta U, which is U final minus U initial, is equal to Q minus W. Now let's think about what these things mean. Remember, in terms of an ideal gas, we've already seen that the internal energy is basically a measure of the internal kinetic energy of the gas. So we're just talking about that 3/2 nkt for the ideal gas. Now, how can we change that internal energy? We can do something with heat. We can do something with work. Now, what are these? What's Q and W? Q is the heat added to the system. So this is very important. It's the heat added to the system. If we add heat to the system, Q is a positive number. Well, if we add heat to the system, we expect its internal energy to increase. So yes, a positive Q gives us a positive delta U. Adding heat to the system increases the internal energy. Then W is the work done by the system. Now this is important. This is by the system as opposed to work done on the system. If the system does work, it is losing energy. When the system does work, it loses energy. So if the system does a positive amount of work, delta U is going to decrease. It loses energy. So delta U will be negative. If the system does a positive amount of work, this negative sign tells us that U will decrease. So we've got to be very careful about how Q and W are defined. Q is the heat added to the system, and W is the work done by the system. So if energy is taken from the system, if we remove energy from the system, Q will be a negative quantity. So Q can be positive or negative. If we add heat to the system, Q is positive. If we take heat from the system, Q will be negative. Likewise, W can be positive or negative. If the system does work, W is positive. If we do work on the system, W will be negative. So when the system does work, W is positive and U decreases. If we do work on the system, then W is negative and delta U will be positive. So if we do work on the system, the internal energy of the system increases. Okay, great. That makes sense. So we've got to be very careful. Remember that delta U is Q minus W. U is the internal energy of the system, and then Q and W are defined such that Q is the heat added to the system, and W is the work done by the system. Okay, let's stick some numbers in here. So again, dealing with an ideal gas, let's imagine we've got that container with the piston in it again. And let's imagine that Q is equal to 7.5 times 10 to the 3 joules. So what does this mean? Q is positive, so we're adding heat to the system. So again, maybe imagine we've got a flame here or something. We put a candle under there. We add some heat to it, but we do it very carefully so we know exactly how much heat we're adding. 7.50 times 10 to the 3 joules. W is 5.00 times 10 to the 3 joules. So what does this mean? The system is, W is positive, so the system is doing work. The gas is doing work. How is it possible for an ideal gas to do work? Remember, work is a force times a displacement. So when we define work, we've got W equals F delta R cos theta, where, remember, theta is the angle between the force and the displacement. So how can a gas, an ideal gas in particular, do work? Well, can it apply a force? Well, yes, the ideal gas is applying a pressure. So we know that it's exerting a pressure here. So there's a force. If pressure is force per area, the force will be the pressure times the area. Well, can it move something through a displacement? Yes, if the piston were allowed to move up, in other words, if the gas expanded, then the force would do work. So if we allow the gas to expand, if the gas expands, pushes on the piston and causes an expansion, then it's doing work. And the work will be the force, which is the pressure times the area. We'll call this the cross-sectional area here. And the displacement here, some delta R. So the work will be the force, the pressure times the area, times the displacement delta R, delta lowercase r, sorry, I wrote delta R. But what is the area times this distance? Well, that's the change in the volume. That's delta V. So this is P delta V. So a gas can do work by an amount, the pressure times the change in the volume, P delta V. This is assuming that the pressure is constant. If it's not constant, then we have to integrate the force with the varying pressure as it changes. But the idea is that if the gas expands, it's exerting a force, it's moving something through a distance, a displacement, the piston, so it's doing work. We'll come back to exactly this value in just a minute. But that's how a gas can do work. Let's say it does an amount of work of 5.00 times 10 to the 3 joules. So what's the change in the energy? We know that delta U is Q minus W, or 7.5 times 10 to the 3 joules, minus W, minus 5.00 times 10 to the 3 joules, leaves us with 2.5 times 10 to the 3 joules. That is the change in the internal energy. Remember, the internal energy for an ideal gas is nKT, so the change in the energy, assuming n is constant, is just going to be 3/2 n delta T, the change in the temperature. So if this is positive, this must be positive, and the temperature, delta T, must be positive, so the temperature is increasing. If delta U is positive, we have an increase in temperature. Oh, that makes sense. What if, on the other hand, let's say the work done were maybe bigger than this, let's say 1.000 times 10 to the 4th, then we would have 7.5 times 10 to the 3rd minus 1.000 times 10 to the 4th. Now the work done is larger than the heat added. We're going to get a negative delta U. A negative delta U will mean that delta T is negative. In other words, the gas is cooling down. So we end up with a positive delta U, the gas heats up. We end up with a negative delta U, the gas cools down. Okay, very, very good. Let's take a look at some examples of the first law of thermodynamics for some of those processes that we talked about before.